Okay.
Okay.
Recording.
Cool. We're recording audio. So, sync test. Cool. That should do that. All right, everybody. Welcome back. Now we are going to take our chromatography paper out of these jars. We're going to calculate our retention factor values, and then Bridget's going to cut out some bands, and we will extract the pigments from them. So why don't we go ahead and, once again...
So they actually look really pretty.
They look pretty dang nice. I'm pretty pleased.
And this one is the one that we did last, which hasn't run very far. You can see the solvent front is about over here, whereas these ones, the solvent front is right near the top.
Yes, we've nearly reached the end of the paper. Just while we've got acetone.
Don't breathe while we...
Oh yeah, don't put your nose in this and just inhale. It's a bad situation. Okay.
Those lids back on.
Yeah, that smell. Woo! Okay. It's not the time for a cigarette break. Don't just swoop.
Alright, so I'm going to undo the staples.
Okay. And there is a very nice sheet. Now, immediately you want to mark how far your solvent front traveled, because as the fluid dries, you will lose that point. Now you only need that for your RF values, so since Bridget is cutting bands, you won't necessarily need that. But let's go ahead and do I'll do some measurements.
Let's just point out the band. So there's I'll hold it over here. So there's a band right up here that seems to have gone exactly with the solvent front.
Yes, and on page 7 of your protocol, you can see that would probably be carotene.
Yeah.
Which
Kerotine's
has
small and it's non-polar.
Exactly. It has an RF value of 1, meaning that this distance is equivalent to this distance. So the band is the same distance from where you began as the solvent front. One number divided by itself is 1. Right?
Right, and then the next one was
chlorophyll A.
Chlorophyll A and B, and xanthophyll migrates with a 0.7. So I'm predicting that the xanthophyll is going to be this yellow one right there.
That makes
so
sense to me.
You can see it over here. And then of the 2 chlorophylls, it looks like
A should go further.
A should go further. So that's this beautiful green color. And then the darker, kind of more olivey green is going to be the chlorophyll B.
Yeah. And if you actually look briefly at page 3 of your protocol, you can see the reason for this. Chlorophyll A and chlorophyll B are essentially identical to each other, but chlorophyll A has a non-polar methyl group at the top right, whereas chlorophyll B has a more polar, what is it, a hydroxyl group? Carbonyl group. There we go. Awesome. So that means that in a non-polar solvent like acetone, the less polar molecule will move further in the solvent because it dissolves more effectively. So that's why that's why chlorophyll A moves a little bit further.
And why would you say the carotene went so far?
Well, probably because it's very, very small.
Much smaller.
And it's non-polar.
Yeah.
So it just moves right along with the solvent. It doesn't get caught up in the fibers of the chromatography paper, etc.
All right. So I'm going to cut, you're going to measure.
That's how we're doing it. First one's nice and easy. It's a 1. I don't even have to calculate that.
Okay. I didn't get the scissors, which I misplaced.
Oh, they are right
Oops.
here.
Thank you, sir.
No problem.
All right, so I'm just going to try and accurately cut as neat as I can along the line.
Okay. So I'm measuring for the first one. It's really easy. The value is the same for the band and the solvent front, which is about 14.8 centimeters. Perfecto. Okay. Now my second band, which we're kind of predicting is going to be xanthophyll, it has traveled. Oh, we can actually take our goggles off.
Oh yeah, good point.
Whew. Okay. So xanthophyll here
If I can.
has traveled about 7 centimeters on the paper, that distance there. I'm going to divide it by the full distance the solvent traveled, which was 14.8. Okay. Great. Okay. And my next band traveled about 3.5 centimeters. And the lowest band traveled about 2.5 centimeters. Good, good. So, with each of these migration values that I just measured, how far the bands moved, I just divide it by the solvent front value. In this case, that's 14.8 centimeters. And I get the retention factor. Now, it is important to note that the retention factor has no units, and I will demonstrate that on the board really briefly here. Very good. Okay, my retention factors have now been calculated. So, let's say I'm calculating a retention factor, and one of my examples would be 7 divided by 14.8. But something you should really get comfortable with is including units when you do calculations like this. It'll be incredibly valuable if you get in this habit as soon as possible. So, 7 centimeters, 14.8 centimeters, and if you're not comfortable with this concept yet, we will talk about it in lectures and labs, the units cancel out. So we end up with a unitless value. It's just a ratio, basically. And your value will be somewhere between 0 and 1. All right? Fantastic. Now, as usually happens in this lab, my retention factor values aren't quite synced up with the typical retention factor values, but the pattern is the same. So the relative distances traveled can be used really to estimate what the pigment is. All right? So we kind of know what to expect, to be quite frank. But that's exactly how you would calculate retention factor values from a chromatography experiment. And how are those bands doing over there,
Yeah,
Bridget?
so right now I am pipetting 5 milliliters of 95% ethanol, into each one of 4 tubes. And I'm going to put the little cutouts that I just made into the tubes to extract the pigment from the paper into the ethanol.
Stupendous.
Alrighty, so this is what my top band, the nice neat one at the top, looked like. That one was easy to cut out. And this is the middle one, a little bit less easy. And then this was the really fun one.
Oh yeah, look at that.
And then this is the darker olive green one, which we predict will be charcoal B.
Stupendous.
So I'm going to break them into smaller pieces so they fit in the tubes. Maybe a little bit smaller than that.
And normally we just number these based on their order from the top going down,
Yeah,
right?
so
2, 1 would be the predicted carotene band, et cetera, et cetera.
So there it is. And you can see, I'm not sure if you can see, but the color is kind of coming out of the paper very rapidly and into solution. So we'll let that, if you can hold that, or...
No problem. Yeah, so a non-polar molecule is going to rapidly dissolve. In fact, the rates at which these pigments are extracted from the piece of paper can even be measured as different because of how soluble a small non-polar molecule is. It's all pretty interesting stuff, quite frankly.
So there's the carotene. I'm going to keep them in order here so that we don't get confused. this is the chlorophyll, probably chlorophyll A.
I'll even actually, I'm going to move this close to the lens so they can see what this sort of looks like up close. Here we go, just hovering in out of nowhere. You can see how the pigment is going back into the solution. Stupendous.
Okay. So that goes in that position.
Very good.
It's difficult to get this one in because it was thick.
Yeah, yeah. Oh yeah, some students I've seen take 20 minutes for this step because they dice it up as fine as they possibly
I'm
can.
doing this quickly.
Yep.
All right.
Cool.
So we now have our 4 extracts. I'm going to vortex them real quick, just to get as much out of there as possible.
Very good, very good. And we're going to be, you've already been introduced.
I'll bring the vortex over here.
Nice, that'll be nice to show them that, yeah. So you've already been introduced to spectrophotometry in the earlier labs, but what we're going to be doing is something a little bit different this time. We load the samples onto this 96 well plate that you can see here. Okay, it looks like the wells have no bottom, but in fact they're just very clear because each well is going to be used like a spectrophotometer, where light will be passed through the sample sitting in the well, and an absorbance and transmittance value is calculated. So when you're running a lot of samples and you don't want to get the spectrophotometer out for each one and use a little cuvette, we use
And
these
then you would
96
have to
well
measure
plates.
the wavelength.
At every single
So
step.
we're going to measure it at 5 nanometer
Yeah.
increments.
So we'll be getting absorbance
Keep it all
values like
visible.
here.
Yeah.
And that'll allow you to actually create a graph just like this absorbance spectra thing. Yeah.
All right, so I'm going to vortex these just to make sure I get as much out of there as possible.
Look at it go.
There's the carotene.
This is it's a very satisfying thing. I just love watching a vortex work.
I don't know if you can see that. Think that's good?
I think it looks nice, yeah. Oh, that one's looking great.
Yeah.
All right.
All right.
Stupendous. Oh, there's also something very important everybody should know about a vortexer. When you get your thumbs really sore from using the pipette too long, it's a massager. That might be one of the most important things you learn out of this lab if you end up working in academia.
All right, so what I'm going to do now is I'm going to take the P200 and the micropipette. I'm going to set it on 200.
So just a quick reminder, everybody, the names come from the maximum microliters that you can pipette at a given time. So a P200 can cover a range of 20 to 200 microliters.
So I'm not sure if that shows up, but that's set on 200 microliters. I'm going to put a little tip on here. And I'm now going to pipette each of these in order into the, oops, didn't go all the way to the bottom.
And this is when, if I was a prankster, I would be bumping Bridget's elbow and goofing on her pretty hard. But that's undergrad stuff. We don't do that anymore.
Come on. Alright. I'm not going to change pipette tips.
No,
Yeah,
that's
we're gonna
completely fine.
conserve.
Yeah. So you're going to be able to access on Canvas a complete data set here. You follow the steps on pages 9, I guess, about 9 through 10, through 11 on your protocol, and you'll be able to see how to graph this assignment. We do expect a lot of students to have trouble with Excel for graphing this. That's completely normal. Everybody kind of has a hard time with this step. if you're having trouble, reach out to your TA, reach out to us, come to virtual office hours, and we can give you some Excel tutorials, which quite frankly is one of the most important skill sets that I acquired in undergrad, was learning how to work with Excel. You'd never get away from it if you stay in research, so this is a good chance.
The sooner you embrace it, the better.
Yeah, don't try to fight it. Get away from Google Sheets and their weird Excel knockoff. It's just not quite as good.
Alright, so here are our samples. Maybe you can take a photograph of.
That's a great idea. I'll upload a photograph of this to the Canvas page.
Need a white. Here we go.
Let's put it on the protocol. Very nice.
Does the color come out?
Just a bit. I'll pick the best one here I can get. Yeah. So basically, we've got a few of these little wells. They're filled up with now ethanol and pigment.
Mm-hmm.
So we'll put this into a well reader, a 96 well plate reader. What's the name of that device? It's got a fancy name.
It's called the Spectra Max, and what it
there
does,
you go.
it shines the light from the top, and it measures in this case, it actually measures absorbance.
Yeah, it directly, you can measure it, yeah.
And so how much of the light at a particular wavelength gets absorbed by the solution.
Yeah. And it's an incredible machine. It can work through a full plate like this in a few hours and just do something that would take us in the lab days.
Yes.
So yeah.
Alright.
This concludes, I think, our photosynthesis lab.
Have fun doing that Excel assignment.
Yeah.
Let us know if you have questions.
Yeah, great. The end.
Yeah, thank you.
Bye-bye. Cool.
Alright, went down.
Yeah, I gotta say, I think it went well. I think we worked out most of the kinks and stuff. Okay.